Hello, my name is Alex Yu. Today I'd like to present to you my research titled Execution Monitoring for Robotic Pruning Using Force Feedback. Dormant pruning is one of the costliest processes of the fresh market fruit production cycle, aside from the picking of the fruit itself. And this work is arduous, it's labor intensive, and it's very seasonal, meaning that you may not have the workers right when you need them. And this motivates the possibility of robots being able to fill the gap for us. In our previous work, we demonstrated a robot pruning system that was able to use visual feedback from a depth camera in order to accurately guide the cutter towards the branch. However, one big drawback of our system was that the only source of closed-loop feedback that we used was position estimates from the camera. And in particular, we didn't consider any of the forces from interacting with the environment. And this led to situations like this, where the robot applied excessive force to the environment, which led to damage to our setup and potentially could lead to damage to the robot itself. Force feedback is an important part of task execution since it provides more robust information about contact with the environment than vision can provide. And so our current research is a preliminary look into how we can use force data to increase our pruning success. Our first task was to investigate if the force feedback readings alone would be able to distinguish between execution successes in which we successfully get the branch inside of the cutters versus failures. The experimental setup we used is shown here with a set of mock cutters attached to a Universal Robots UR5E robot arm. Our test setup is shown on the right. It's built to resemble a specific type of sweet cherry tree. The experimental procedure that we used consisted of selecting a target on one of the horizontal branches and having the robot move to an approach pose about 10 centimeters away from the branch. And once it was there, we would then move in the cutter linearly towards the target point. And while it was moving linearly, we would record the end effector forces as the cutter interacted with the environment. After we collected the data, we labeled all of the force readings we got and then trained an LSTM neural network to take in these force readings and output a confidence value representing its belief that it was either succeeding, failing, or that it was unsure about its current status. An example of this execution is shown in this video over here. You can see that as the arm approaches, it updates its belief as we establish contact. And in the end here, it believes that it has succeeded based off of the force profile. Our first goal was to analyze the force profiles of the successes versus the failures to see if there were any major differences. And shown here are heat maps for all of the force readings labeled as successes and then failures. We only show the y and the z forces here since those were the most dominant forces overall. The y is in the up-down direction while the z is in the in-out direction. Our expectation was that if the branch missed the cutter, that it would apply a large force either up or down in the y direction, whereas in the success case, the dominant force should be in the z direction from the branch pushback. And this is indeed the trend that we saw. We see that failures tend to be accompanied by high magnitude y values, either positive or negative, while successes tend to be more concentrated within the low y force region. And the LSTM that we trained is able to pick up on this to perform robust and quick state classification, correctly identifying the terminal state for 8 out of 9 of our test episodes, as well as achieving an accuracy of about 80% on all of the force readings aggregated together. Now, we do note that our sample size was relatively small for these experiments. And so, in the future, in addition to gathering more data, we would like to explore how to make our system more reactive and more robust overall. One idea is to use active perception to have the robot take actions which better inform its current execution state, such as this wiggling motion, which is able to tell the robot here that it is successful. And then our ultimate goal would be to integrate this force feedback system with some sort of vision system which can guide the cutters towards the branch using only 2D images and even with imperfect calibration. And then somehow we can gracefully transition from the vision-based controller and hand it off to the force-based controller as the robot approaches the branch. Thank you.